Welcome students. In this lecture, we learned semiconductor. The previous lecture started chapter electronic component and we already learned passive component, resistor, capacitor and inductor. Now in this lecture, we learn semiconductors. The semiconductor are those substances whose conductivity lies in between that of conductor and insulator. For example, silicon, germanium, gallium, arsenide, etc. In terms of energy bands, semiconductors are those substances in which the forbidden gap is narrow. So the semiconductor lies in between conductor and insulator. So the conductor having low resistivity, whereas the insulator having high resistivity, and semiconductor having intermediate resistivity. Semiconductor classified into groups: intrinsic semiconductor and extrinsic semiconductor. Firstly, we see the intrinsic semiconductor. Intrinsic semiconductor in an extremely pure form. There is no any impurity is added. These are the extremely pure form is known as the intrinsic semiconductor. For example, silicon and germanium. These are the intrinsic semiconductors. Both silicon and germanium are tetravalent. That means it's having 4 valence electrons. Each atom form a covalent bond or electron pair bond with the electrons of neighboring atom. See the crystalline structure of silicon or germanium at low temperature. At the low temperature, all the valence electrons tightly bounded the nucleus. Hence, no free electrons are available for the conduction. The semiconductor behaves as an insulator at the absolute zero temperature. This is the silicon or germanium nucleus. These are the valence electrons. See the next diagram. In this diagram, crystalline structure of silicon and germanium at room temperature. At the room temperature, some of the valence electron gain thermal energy to break up the covalent bond. This breaking up covalent bond set the electrons free. Here, breaking the electrons set the covalent bond is free and available for conduction. When electron escape from covalent bond and become a free electron, a vacancy is created in a covalent bond. See, this is a covalent bond due to the thermal energy. Here, vacancy is created, and such a vacancy is called hole. Such a vacancy is called hole. It carries positive and move under the influence of electric field in the direction of electric field applied. The number of holes are equal to the number of electrons, since a hole is nothing but the absence of electron. After that, we see extrinsic semiconductor. When an impurity is added to intrinsic semiconductor, its conductivity changes. This process of adding impurity to a semiconductor is called doping. This process is called doping, and the impure semiconductor is called extrinsic semiconductor. When impurity is added, this process is called doping, and this impure semiconductor is called extrinsic semiconductor. Depending on the type of impurity added, extrinsic semiconductor are further classified: N-type semiconductor and P-type semiconductor. Now, firstly, we discuss N-type semiconductor. When a small current of pentavalent impurity is added to a pure semiconductor, it is called N-type semiconductor. The addition of pentavalent impurity provide a large number of free electrons, and semiconductor crystal. The typical example of pentavalent impurity are arsenic, antimony, phosphorus, etc. Such impurity which produce n-type semiconductor are known as a donor impurities because they donate or provide free electrons to the semiconductor crystal. See the energy band diagram for the n-type semiconductor. See here, so the silicon and arsenic. To understand the formation of n-type semiconductor, consider a pure silicon crystal with impurity arsenic. We know that silicon atom has a 4 valence electron and arsenic has a 5 valence electron. When arsenic is added with silicon, the 4 valence electron of silicon make a covalent bond with 4 valence electron of arsenic. The 5th valence electron find no place in the covalent bond. Thus, it become a free and travel to conduction band. Therefore, such arsenic atom added 1 free electron will be available in the silicon crystal. Through this arsenic atom provide free electrons, an extremely small amount of arsenic impurity provided through atom to supply million of free electrons. Due to the thermal energy, still whole lecture pair are generated, but the number of free electrons are very large. Number of free electrons are very large in numbers when compared to holes. So in n-type semiconductor, electron are majority charge carries and hole are minority charge carry. Since the current conduction is a predominantly by free electrons, it is negatively charged. It is called n-type semiconductor and means negative. Now, next is a p-type semiconductor. When a small amount of trivalent impurity is added in p-type semiconductor, small amount of trivalent impurity is added to pure semiconductor. It's called p-type semiconductor. The addition of trivalent impurity is provide large number of holes in semiconductor crystal. For example, gallium, indium, or boron, etc. Such impurity which produce p-type semiconductor are known as a acceptor impurity because the holes created can accept the electron. These holes can create accept the electron in the semiconductor crystal. See the energy band diagram of p-type semiconductor. See here in the diagram, to understand the formation of p-type semiconductor, consider a pure silicon crystal with impurity gallium added to it. We know that silicon has a 4 valence electron and gallium has a 3 valence electrons. When gallium is added impurity to silicon, 3 valence electron having covalent bond with silicon and 4th valence electron of silicon cannot make covalent bond with gallium. Cannot make covalent bond with gallium because gallium having only 3 valence electron. The silicon cannot make covalent bond with this 4th electron because short of 1 electron. See here the diagram, short of 1 electron, and this absence of electron is called hole. Therefore, each gallium atom added 1 hole is created a small amount of gallium provide million of holes. So the conduction band, forbidden gap, valence band, due to thermal energy, still whole electron pair are generated, but number of holes are large compared the number of electrons. Therefore, p-type semiconductor hole are majority carries, and p-type semiconductor hole are majority carries, and electron are minority carries. So the current conduction is predominantly by holes. That is called p-type semiconductor. P means positive. After that, see the p-n junction diode. When p-type semiconductor material is suitably joined to n-type semiconductor, the contact surface is called p-n junction. The p-n junction is also called as a semiconductor diode. See the p-n junction diode. See here the left side material is a p-type semiconductor having negative acceptor ions and positive charge hole, and right side material n-type material semiconductor having positive donor ion and free electrons. Suppose these two pieces are suitably treated to form p-n junction, then there is a tendency for free electrons from n-type to diffuse over p-side holes from p-type to the n-side. This process is called diffusion. As the free electrons move across junction n-type to p-type, positive donor ions are unconverted. Hence, positive charge is built on n-side. Hence, positive charge built in n-side of the junction. At the same time, free electron cross the junction and uncover the negative acceptor ions by filling the holes. Therefore, negative charge is established on p side. Negative charge established on p side of the junction. So the outside this barrier on each side of the junction, the material is still neutral. Only inside the barrier, there is a positive charge on n side, negative charge on p side. And this region, here, this region is called depletion layer. This region is called depletion layer. The logic symbol of p-n junction. In connecting a p-n junction to an external DC voltage source is called biasing. Two types of biasing, forward biasing and reverse biasing. So the forward bias, the voltage potential is connected positive to the p-type material and negative to the n-type material across the diode, which has effect of decreasing the p-n junction width. And reverse bias, the voltage potential is connected to negative to p-type and positive to n-type material across the diode, which has the effect of increasing the p-n junction width. The first, forward bias junction diode. When diode is connected to forward bias condition, the negative voltage applied to the n-type material. See in the diagram, negative voltage applied in the N-type material, and positive voltage applied to the P-type materials. Here, positive voltage applied to the P-type material. This is because the negative voltage repel electrons towards the junction. Thus, the negative voltage pushes or repel the electrons towards the junction, giving them the energy to cross over the combine with the holes being pushed in the opposite direction toward the junction by positive voltage. See this diagram. This is the negative, N-type, P-type. This is a PN junction, that is this region, deflection region is here. Due to in the forward bias junction, reduce the deflection layer. Reduce the deflection layer. So next is a reverse bias junction. When diode is connected to the reverse bias condition, positive voltage is applied to N-type. See in the diagram, positive voltage N-type, P-type, positive voltage applied to the N-type and negative voltage applied to the P-type. Positive in N-type and negative in P-type region. The positive voltage applied to N-type material attract the control. Here, when negative voltage is the positive voltage applied to the N-type material. Here, positive voltage applied to N-type material attract the electrons towards the N-type region, whereas the negative voltage attract to the positive voltage towards the positive electrons. Due to this, wider or increase the deflection layer is here. So the electrons towards the positive electrode and away from the junction, while hole is P-type N are also attract away from the junction toward the negative electrode. See in the diagram, that's why deflection layer is increases in reverse bias. Okay. This is the logical diagram. Okay, so we will stop here. Thank you, students. Next lecture, we learn Zener diode, LED light emitting diode. Okay, so thank you.